Hello, everyone. Thank you for joining us for tonight's preservation school about all the architectural metals. We will have more preservation schools and virtual Six Celebrate tours throughout the winter. Information on all of our upcoming programming can be found on our website, hdc.org. If you have any questions about programming, you can contact me, Michelle Arbulu, at marbulu@hdc.org. Tonight's class will be recorded and posted to our YouTube channel for free viewing. You may also watch all of our previous preservation school classes and virtual tours on our YouTube channel. I would like to thank the New York City Department of Cultural Affairs, City Council, the New York State Council on the Arts for supporting Preservation School. Now I will hand it over to Kate Allen, the president of Allen Architectural Metals. Thank you.
Hello, thank you so much for having me. I'm really thrilled to see how many people are here today. My name is Kate Allen. I am president of Allen Architectural Metals, like Michelle said. I took over 2 years ago from my father. Our company is nationally recognized ornamental metal company, 28 years. And we recently just became a nationally certified WBE, and we're currently seeking certification in the state of New York. A couple of our recently completed projects, the Harlem Fire Watchtower, the Equitable Building, which is 120 Broadway, 422 Fulton in Brooklyn, the Macy's Building, and currently we're working on the Lincoln Memorial Undercroft exhibit in DC, Carnegie Hall, the Monumental Fire Escape restoration, New York Historical Society bronze window restoration, and the Waldorf Astoria. We have quite a bit of work there in both ornamental metal restoration as well as new fabrication and a lot of custom metal work at that project. So just a little bit, today I wanted to speak about cast iron because that's the alloy that I work with the most. I think what's important to know is that cast iron is a generic term. It designates an entire family of metals with a wide variety of properties. So cast iron, simply put, is liquid iron that is cast and put into a mold and allowed to cool. It's defined as an alloy with high carbon content, about 2 to 5%. In addition to carbon, cast iron has to contain silicon, about 1 to 3%, and then when combined with carbon, it gives it excellent castability. It is hard, brittle, and non-malleable, and it's more fluid than steel. As you know, cast iron has been used as an architectural ornament in America since the 18th century. It still persists today. Early 1800s, we see things like fence posts and stairs and balconies. 1820s, we see the first cast iron columns being introduced into storefronts. 1825, we see an advertisement for a cast iron ground floor shop in Burling Slip down in the South Street Seaport. And then about the 1850s to 1890s, we start seeing the prevalent cast iron facades that we identify with Soho and the cast iron district. We see some of these going into the early 1900s, but really it was the material of choice through the late 19th century. So all historic cast iron is gray iron. It's a common traditional form. It's very easily cast, but not forged or worked mechanically. So when gray iron is broken, the fracture occurs along the graphite in that iron. And gray iron is still forged today. It's made by remelting pig iron, which is basically just scrap iron, steel, and other materials, and then you take out the undesirable contaminants. More recently, we see and use a lot of ductile iron. It's sometimes referred to as nodular iron or spheroidal graphite iron, patented by Keith Mills in 1948. The graphite form of ductile iron is spherical, as I mentioned, compared to the flake form of gray iron. And what you need to understand is that ductile iron just has much better material properties. The composition of ductile iron is silicon, an alloy agent, silicon magnesium, carbon, and iron. And so ductile iron is really known for its strength, and its toughness and its ductility. And as I'm sure all of you know, ductility is simply put just a material's ability to bend. And the properties of ductile iron far exceed that of gray iron. So we tend to, in certain applications, this is definitely the preferred iron of choice for us. And we'll get into like when that's the right decision and when it's not in a minute. So here's a cross section of gray iron versus ductile iron. You can see the flake-like shape of the gray cast iron. I think it would be your left. And then the more spheroidal shape for the ductile cast iron. It's much more impact and fatigue resistant. And the cast gray iron is weak in tension and strong in compression. And ductile iron really seeks to correct that deficiency. It's about 5 to 10% more expensive than cast gray iron. And there are less boundaries that you can find to run small runs, meaning, unless you're going to run 100 of something, you're looking at a more art foundry type application, and they're going to run smaller runs, 10s and 20s of things. Okay, so I want to talk a little bit about pattern making because that's a big part of what we do. Okay, so 3 ways to make castings. One is to use the original casting to create the pattern. Number 2 would be to create a new pattern from drawings or historic photographs, which we do very frequently. And the third would be to hand scan an existing piece in the shop or in the field. We have a EVA for larger castings that we use for all of our hand scanning, and we have a Spider for smaller castings. More recently, we've been incorporating a lot of 3D printing into our pattern making to kind of keep up with volume and schedule demands. We've kind of exploded in growth, and we're really utilizing a lot of 3D printing now and exploring ways to make that more efficient and effective in our day-to-day operations. So our pattern schedules, just if you're wondering about like a typical project and what that looks like, pattern schedules typically depend on the quantity and the complexity of the project, and they run somewhere about 4 to 6 months after shop drawing approval. So you got to give yourself 3 or 4 weeks for shop drawing approval. And then after the patterns are completed, you're looking at somewhere between 6 to 8 weeks for casting and foundry schedules. And so the typical project is going to run anywhere between 9 and 18 months, depending on the size. I just think that's important to know. A lot of times people don't understand how long it takes to produce something. And I think having realistic expectations that, this is not something that happens overnight is important. So on the left here, this is the original casting. This is like a piece that we take from the site. To the right, you see a piece that has been sandblasted, and you can see the difference in the texture. And at the bottom, you see this is a blasted casting that's had body repair. So we basically use like an Evercoat body filler to smooth out imperfections before it becomes a pattern. So the original piece, then this has been primed and it's set on a pattern plate. And we're basically preparing this for the mold. The pieces that are surround the primed piece, that's called the form. And we use tree wax as a release agent. So we're going to, coat the piece in the tree wax. We're going to pour a 2-part polyurethane plastic to create a negative impression. And that's on the bottom is what we're doing. So on the top left, you can see that negative mold in the original casting to the right. So then you're going to continue to fill that negative cavity. And like in this case, it would be inefficient for you to run 1 casting when it's this small. So in this case, we're going to create something called a 4 impression pattern. So you're going to get 4 castings out of every pour. We also call it a 4-on pattern. And again, we're using tree wax as that release agent. So here are the 4 pieces, and we're doing it again. Maybe not. Okay. So here at the top right, the 4 impressions have been, now they're mounted onto the pattern plate. And in the center of that pattern plate, you see something called a gate. That gate creates a passageway. And in a minute, you'll see what I'm talking about. When the sand is packed around these forms, that gateway creates the path for the molten iron to flow into those negative cavities and fill the void and become the castings. So you're basically, after you mount the pattern plate with the 4 primed pieces, you're going to add, you're going to prime them. You're going to build a box. On the left, the flat part of the box is called a cope, and on the right, it's called a drag. Um, in the industry, we call this a dump box because you're literally going to pack it full of sand and you're going to dump it over, very straightforward. A wooden pattern like this can be used like 1,000 times. Okay, so here on the top right, after you get the cope and the drag box together, you're going to coat it with something called zip slip paint, which is basically a non-binding release agent. And then you're going to pack this air set sand into these boxes. It's just a chemically bonded sand, and then you're going to spray it with a graphite wash. Basically, you're going to take the cope and the drag, you're going to stack them on top of each other. First, you're going to spray them with a graphite wash. You're going to set it on fire for about 10 seconds. This gives the castings a nice crisp feel, and it smooths out the edges. And so you're going to put the drag on the bottom, the cope on the top. You can see that gateway on the top right. That's the gateway you created to create that pathway for the molten iron. And then you're going to, the hole that's in the center is called the sprue. And the molten iron is going to come down through the sprue, fall through the gate, and fill those negative cavities and become the positive casting. The iron comes out of the furnace anywhere between about 1,200 degrees to 2,100 degrees to 2,500 degrees. And different molds are poured at different temperatures. So like the thinner the casting, the lower the temperature. But it's really important that you have controlled cooling to prevent the casting from cracking. So you have to bring that temperature down slowly. Typically, a casting will solidify in about 5 minutes, and it comes out of the mold in about a half an hour. But larger castings, they may sit up for 24 hours. It just really depends on the size. And the desired cooling is always based off wall thickness. So we typically pour castings somewhere between 3/8 of an inch and an inch. So here are those that 4-on casting coming out of the sand, and you can see the gating is still attached to the castings. And so all molten metals, they shrink as they solidify. So we have to account for shrinkage and draft in all of our pattern making. And a rule of thumb is for shrinkage is about 1/8 of an inch per linear foot is what you have to account for. And this is a really critical point for larger casting. So, like right now, we're trying to show an example, trying to give the architect an example that we've copied, that we've replicated an original casting accurately for the new patterns. Well, the new patterns are larger than the original casting. So we have to explain, the foundry process to them to say, please don't ask, well, these aren't the same size. No, they're not, because we have to accommodate for that shrinkage in the foundry. So that's something that sometimes people don't know. And it's very difficult to find pattern makers today. It's really becoming a little bit of a lost art. It's even more difficult to find pattern makers that have a knowledge of foundry practice and castings. And that's the need. That's why we have the need to really incorporate this 3D printing and technology. But traditional pattern making will always have a place, in my opinion, in ornamental metal manufacturing. I think it'll aid the industry, but I just don't see it ever disappearing. Maybe. So at this step, you're just going to knock off the gating. You're going to clean up around the edges, and then, rebuild the fabrication of the element that you need. So when we arrive on site, a lot of the typical failures that we see are coatings, fasteners, major structural failures, a lot of rust jacking, and a lot of material loss. So here, this is 361 Broadway, James White Building, 1881, Italianate style. On the left, you can see the capitals have fallen off. Typically, you're always going to see damage at where the fasteners are located. That mild steel starts to corrode, and then the ornamentation starts to fall off. On the right, this is 287 Broadway, James Snook Building. Both of these buildings have been very well restored. One by my firm and one from the one on the right is Historical Arts and Castings, also excellent ornamental metal company. But these are just, this is an extreme example of deterioration. Basically, a building was being put up next door and the entire building shifted. And so when it shifted, the building failed. It literally broke in the middle, like down through the middle. So the entablatures, the water tables, all the support brackets, everything, and you could go floor to floor. It was crazy, and everything was broken. So that was a really complicated restoration. I'm really glad to see that they were able to save it. Here's more. This is 93 Reed Street. You can see the abacus, the bell, like right in the center where that mild steel fastener is. It's just corroding and breaking away. Water infiltration, poor flashing, poor maintenance over time. These are this is what we see mainly because it's a ferrous metal, right? Water, it's the enemy. More failures on the top left. This old Chicago post office in Chicago, Illinois. Heavy corrosion, salt, dog pee, all this wears down, but breaks down the coatings first and then starts to degrade the base metal. Bottom left, the same way, water infiltration, maybe casting section loss, maybe just the materials getting thinner over time. Top right, Fox Theater, in Detroit, where I live, go Lions. But you can see here that what's happened in this case is got really bad no waterproofing, no sheet metal flashing. So basically water is pouring down that vertical mullion. It's kicking that plate out, pushing that picket forward, and that jack rust is just, the rust jacking is just building up, and it really needs to all be taken apart, needs to be treated, needs to be waterproof. But I went over there last week, and they just put another lovely layer of paint over it. So it's not getting the attention it needs, unfortunately. Maybe one day. All right, these are some of the failures that we saw at the U.S. Capitol Dome. Ornamentation failure again, failing welds, just, typical wear and tear. Okay, so you've got all these failures. Now, how are you going to repair them? All right, these are typical cast iron repairs that we perform on a daily basis. We come to a building typically for one of three reasons. It's either an emergency stabilization, like they've got some kind of liability, something is dangerous. Routine maintenance has been identified. Local law 11 is great, for keeping buildings maintained, or a developer has a project and they're doing like a major overhaul. They've got to restore, and then we tend to do a lot of custom work too. So we'll get into like replications and new storefronts, as well as restoring the existing facades. So these are epoxy repairs. This is from the U.S. Capitol Dome. Epoxy steel is a great cosmetic repair for pitting or surface imperfections or voids. It needs to always be applied to clean material. We use Defcon steel and Defcon stainless steel, I would say 90% of the time. Sometimes the pits and voids are just due to deficiencies from the foundry and during the casting process. So you kind of just have to make a decision of what level are you going to treat, this iron. Do you want it to look flawless? Do you want it to look like fiberglass? Do you want it to look true to itself and be iron? Those are things you have to decide, for yourself. So here is the epoxy repair after the Defcon is applied. You're going to sand it down with a 60 grit sandpaper. And then this is just a straight edge. We're showing that it's flush, and then we're going to prime over it. So there's really no need for stainless DevCon. I mean, if you've got a good 3-coat finish system, I think it's a little overkill. But obviously, at the U.S. Capitol, they wanted it, museum quality, and so they went the extra mile and wanted stainless steel. It's also more expensive. Okay, so any hole that you have in cast iron that's over 3/8 of an inch is pretty much going to signal a threaded rod repair. It's not pitting; it's a physical hole. So when you have this hole, you're basically going to drill it out with a bit that is slightly smaller in diameter than the tap. And then you're going to use the tap to create the threads that the threaded rod will then receive into the hole. So the threaded rod is installed, you cut the excess threaded rod off, you sand it down, you add the epoxy, sand it, and you grind it down, you add the epoxy, you sand it down, and then you paint it. We do a lot of threaded rod repairs. I want to talk a little bit about metal stitching. This technique is typically used to repair ship hulls, like large ships. But it was specified at the US Capitol Dome when we were there in, I think, I don't even remember anymore, 2014, 2016. Yeah. We had a company come from California to train our technicians on this repair. And I just really want to stress this is a really complicated repair. It's very expensive, but I've always thought that this is a terrific repair for preservation projects. As a preservationist, I thought, wow, this is a great way to really save as much historic material as possible. I've been really excited to see it specified lately more. We're working on 2 projects now where there is metal stitching involved. One is Grand Army Plaza, the Soldiers Arch stair. We're performing some metal stitching there, as well as Cape Hatteras Lighthouse and National Park Service. So I'm really encouraged to see this showing up more. What you need to know is that basically the pins are sealing the crack and the locks structurally stabilize it. The advantages to this method is you don't need heat. It's easier to perform in the field, and it's very successful compared to something like welding. It's similar to a threaded rod repair in that, you're tapping a hole and you're adding a pin. It's very slow though. One man can perform an inch an hour. So you think about that on 3/8 inch cast iron. We had 12,800 inches of cracks at the US Capitol Dome. So it was a very slow process. This is just showing some of the metal stitching from the dome. There were cracks not only in both of the interior and exterior domes, but also the boiler plate, which is the area beneath the balustrade. It was hot. We had a ton of turnover. You had to be in hazmat suits. There was lead paint present. DC in the summer, it was brutal. I mean, the fact that we survived and completed it successfully was a miracle. So we're very proud of this project. This is Cami. She's one of our project managers. This is how we identified visual cracks. So we would, mark them on the building, give them a tag, and then we would abate them to see, okay, is this just a surface imperfection or is this actually a physical crack that we need to stitch? Okay, there's the lock and the pins, cross section of that. We use something called an electromagnetic particle test to determine the length of the crack. It's like a sand and a light that you spray on the iron, and then you can identify the end of the crack. And so once you find the end of the crack, you're going to drill it out, and that relieves the pressure and that prevents it from cracking any further. And then you freehand drill the first hole. And then you use a jig that basically guides you along the crack to create the holes. And the holes are where you're going to add those pins, and you're going to torque them to the proper depth, and then they're going to shear off. And then you're going to add the lock, and then you're going to add the pin, and then you're going to add the lock, and then you're going to follow the whole crack that way. And then once everything is completed, it's ground down smooth. Here you can see there's an identified crack, and then there's a completed metal stitching repair. Okay, this is called splicing. This is just when deteriorated iron is cut out and you're going to add a new plate. by welding, or you're going to create mechanical connections with stainless steel fasteners. Okay, so another repair, this is more like a reinforcement, are backer plates. We do a lot of backer plates. The geometry of the piece really determines the backer plate, and this reinforces the connection point. It also helps like with flashing and caulk application. It allows you to prevents any further water infiltration. And also reinforces old repairs. So let's say that you have a weld on the edge, of a piece that's ending, that's meeting another piece. Well, you add a backer plate that reinforces the old repairs, and it just gives more strength in an area that's kind of weakened. This is a combination repair. This is a backer plate and a splice. Again, the deteriorated cast iron is going to be cut out. The new filler piece is going to be put in to match the profile. It's welded around the perimeter, and then the cosmetic repairs follow. But typically we use stainless steel for backer plates, and that should always be isolated with like a 3M Scotch wrap or a neoprene, and then that prevents galvanic corrosion. And then finally, the DevCon is a visual repair, where the backer plate is the structural repair. So Dutchman repairs, so similar to stone, same way, comparable, and that you're replacing damaged or lost sections with similar parts of same geometry and design. This profile can be created by pulling a mold from a neighboring piece, and it keeps you from replacing the entire casting. It's particularly good for cornices and tablatures, on facades, anywhere water is really prevalent. I personally feel like it's a much more permanent replacement and a better repair to do a Dutchman out of iron than like sheet metal, because sheet metal over time the coating will fail, it will get dented. You can see that it was a replacement repair, where these you can barely tell that it's discern the old from the new. Here's another combination repair. This is actually a threaded rod Dutchman backer plate stitching repair. So all of them in one. We created the new Dutchman part and then stitched it in and did backer plates behind the repairs, as well as threaded rod. And so, this is my opinion. We feel that welding's not a great repair for the field. It can work well for heavier castings, but it is really best suited as a shop repair. The need to preheat castings slowly and uniformly is just so critical. It helps reduce the risk of thermal shock on the cooling. And if castings aren't heated and cooled properly, you face the risk of the weld failing, this is what we see. This is a failed weld from the 60s. It's very difficult to do in the field. But too much welding creates hardening. And so this isn't, we basically found this weld at the failed weld at, it's very hard to say, at the Capitol, cut out the damaged section and replaced it with a Dutchman and stitched it in. Some reasons why welding might not be the best choice. It's the heat. The use of heat is objectionable. The material possesses a poor weldability, or it's expensive, or the heating causes hardening, which is kind of what we saw here, which hardening will make the material more brittle and more prone to breaking over time. So you just kind of have to use your best judgment. These are tab repairs. Most important thing about a tab repair is that when you're performing the fastener replacement, which is the new bolt, that the torque is critical. If you over torque the fastener, you're going to create internal stress. It'll ultimately lead in the failure of the tab. So you first cut out the damaged tab. You're going to grind it smooth. You're going to insert your shims, and you need to distribute the bearing force equally. So the shims are very important. Neoprene, again, always used as a barrier between stainless and cast iron to prevent galvanic corrosion. And these are three completed restoration projects using those repairs. James White, 1881 on the left, the cast iron house has a Shigeru Bond addition on the roof. 93 Reed in the middle, one of the oldest surviving cast iron buildings in New York City. If you're into further research, I love Daniel Badger's illustration of iron architecture. I find it be fascinating, and this is plate 15. So I was super excited to work on this building. And then to the right, you know, class 10 gray iron Walter and Meggs U.S. Capitol Dome, built between 1854, 1865. Okay, so I want to talk a little bit about our capabilities for replicating material from historic photos. This is where traditional pattern making plays a major role. This was the last major project by Daniel Burnham in 1912 in Boston. This building was regarded as one of the best examples of Beaux-Arts architecture in the country. And these canopies were installed on this building in 1912. Somehow, some way in the 50s, they were removed, they were scrapped, they were thrown in the trash, never to be seen again. So that we were asked to recreate these canopies from this photo and this drawing. So we spent a lot of time interpreting the photos, and we were able to recreate this canopies over 150 linear feet with the use of sculpting and 3D modeling. Woolworth Building, I'm sure you're all very familiar with this. Cass Gilbert was the tallest building in the world from 1913 to 1930. And in 2016, Alchemy Properties purchased the top 30 floors of this building, and they underwent a major renovation. We were asked, this is the rendering on the right, we were asked to replicate the historic ironwork for the new residential entrance. However, the challenge in this was it would require that we increase the scale by 33%. Rough opening was 33% larger than the Park Place side. So we had to marry a variety of materials and styles and finishing techniques to achieve the desired end goal. So this is the commercial entrance on Park Place, and you can see this is really highly ornate metalwork. Reminds me of a lot of Chicago, the Carson Prairie building. This is the overall design concept. Modern cantilevered canopy, 2 sets of Muntz metal doors, exterior and interior. The largest challenge was trying to achieve, if you can see in this drawing, the 30-inch radius on a 90-degree bend for the curved storefront. We had to have it rolled in Canada. It was also really challenging for the glass manufacturer because they had to bend the glass on a 28-degree radius. And then also for the castings, because the castings had to be curved. Everything had to come together. The design goal was to fabricate the castings out of bronze, but they proved to be far too heavy for the Muntz metal frame. So we suggested that we could make them out of aluminum because it's a third of the weight. We could paint them with a metallic bronze finish and give them the same look of bronze without the weight of bronze. Again, using that 3M tape between the castings to isolate any galvanic corrosions. So we use a combination of hand scanning and traditional pattern making here. This is a 2-part mold making process that we use. Smooth on. And in this case, it was much more effective for us to pull molds from the site rather than scan with a laser. When we did scan with a laser, the level of detail in these castings far exceeded the capability of the scanner. We lost a lot of detail. We were trying to stretch it because, we're trying to accommodate that 33% growth, and things were skewing and parts. The time it would have taken us to fill in all the gaps and to try to make it, it wasn't an effective use of time. So we decided to pull physical molds, and then we could have those patterns hand sculpted and then scaled to that 33%, was actually 35 for these, for the residential entrance. But this way we could put the physical piece like in the sculptor's hand. They can look at it, they can scale it, they know what we're looking for. and they can achieve the end look. So here on the right, you can see some of the clay sculpting. This is our CNC machine cutting the patterns, and you can see that sculpted clay overlay on the top. So you're going to inset that clay overlay into the CNC part, and then you're going to get the finished piece on the right. You pour resin on top of the clay, just like we were talking about with the castings. You know, when you're creating the pattern, it's the same. You're creating that negative, then that negative will become the positive. You can see the clay on top. This is some of the taller vertical castings. They turned out really well. Combination, again, CNC and hand sculpting. And then this piece, this is over the entrance. This piece is huge. It's 7 foot 3 inches wide by 2, 3 3/4 tall. These were the largest some of the largest castings we had made. And you can see the rounded area on the right. That's where we had the worst skewing with the hand scanner. So we utilize SolidWorks. We use SolidWorks and Inventor to anticipate any areas that we were going to have and needed modification, also to develop connection details. This way, you know, we can rotate the assembly, we can look behind it, we can see where problems are going to occur. It also helps us calculate the weight of the overall assembly, which we need. And so here are some of the castings out of the foundry, and they've got that zip slip paint, you know, still on them, that release, that non-binding release agent. I was really pleased with these, but those curved castings were so difficult to pour. We poured them almost 3 times because you have to have the proper venting, and they also have to be hot enough to push that molten metal all the way through that curve. So here's some images of the installation. This is just a rough opening of the vestibule. You can see that the curved storefront. We used a Hilti epoxy anchoring system with stainless steel threaded rods. And this is a coal patina, so birchwood casey in this case. Here are the castings after they've got that, the 3M, before we're installing them, we're putting that 3M tape, that Scotch wrap, which is a polyvinyl chloride tape. It's amazing. It's resistant to salt and chemicals and abrasions and sunlight and everything. And the paint we used is a 1078, a Tennemic Flournoir. We use it all the time now. It's like probably the #1 system that we use the most. It's highly regarded, approved by Landmarks. It's got high UV resistance. It's got anti-fading, streaking properties. It has great color and gloss retention. And in this case, because these were aluminum, we used a Typoxy primer, but had it been iron, we would have used zinc. So there's the canopy. You can see those curved castings being installed. And then these are some of the pictures from the finished product, but they turned out really, really well. I mean, they're just stunning. I'm really proud of this project. We have more photos on our website if you're interested. Okay, so in the 1850s, glass vault lights began to appear in the city as they permitted daylight to reach the dark basements beneath the sidewalk. And so this created more rentable and usable space for building owners, and also gave the storefront more character and street appeal. And so for the most part, these panels are really in a state of disrepair. We see these all the time. We see failing glass. We see structural failure, not only of the panels, but of the framework. And salt and water have really deteriorated both the sealant and the coating systems, as you can see. Sometimes we see asphalt or a cementitious type of material that's been applied to the top of these with the hopes to stop leaking. Well, this is like a terrible idea, because you can imagine concrete, ferrous metals, water, it's very corrosive. So this fix really just accelerates the deterioration. And in a lot of cases, we can't save these. We've tried, you know, to get the concrete off of them, and then the material below is just, it's shot. This is 70 Franklin, that 361 Broadway building we were talking about earlier. There's a tremendous amount of time spent in developing these drawings. We have to replicate, the vault lights, the framework, the panel. It takes a lot of exploratory work to kind of peel away the layers of time and try to find a system that can accommodate all the modern requirements. So like in this case, they wanted to bring back vault lights for a spa for the residents in this building. And it was obviously not part of the original design. And you can see here, this is our 3-inch steel frame with a recessed lip that they support our vault light panels. And then we weld T-bars in perpendicular to create the frame. So the owners had two choices. They could either just pour a concrete pad and then they could put the panels on top and then they could bring in some artificial light, or they could go the more expensive route, which is what they chose, which was the custom designed frame to support the new panels and bring in all the natural light. We always pour these panels in ductile iron. We've actually redesigned and re-engineered these panels to be more efficient, down to the types of grout we use and the tapering of the hole to receive the glass. We have a source that we use for all of our glass in upstate New York. It's fantastic, but we definitely pour these in ductile iron because of that flexibility. The standard sizes that we see typically about 3 to 4, 3'4". They weigh about 200 pounds, and we pour them anywhere between 1 inch to 1.25 inches thick. But we've spent a lot of time developing these and our ability to design and install them. And the challenge with these panels is when they're on the street like this, there's a loading. I don't know what the code is exactly, but you have to be able to withstand one wheel of a fire truck, which is 16,000 pounds. And so that we have an engineer in-house, so we engineer everything and run calculations on it. But that is normally why we had to pour it in ductile iron, and also for the framework has to be reinforced to meet those modern day codes like we were talking about. So different types of vault lights, treads, and risers. Some before and after of these. 361. This is the Puck building. So in this case, the treads were restored, but the frame and the panels were all cast in gray iron, and they were deteriorated beyond repair. And the caulking was failing because all the movement. And so these panels were fully restored. They were restored previously, but they were failing. The glass that they chose to restore them with was very inexpensive. It was very thin. The grout was wrong. So we replaced these panels. Also, the structural support beneath it was insufficient for the weight of these panels. So we saved the structural steel, but we decided to sister and marry a new beam to the old beams to give it more support. We've done 10, 12 of these projects. Feel like we've gotten pretty good at them at this point. So I want to talk finally a little bit about window restoration. This is the Albert Kahn building in Detroit. It's on the National Register, built in 1931. You can just see beautiful bronze double hung windows. I mean, look at the hardware. These windows were slated to just have replacement glass when necessary, just 1/4-inch monolithic glass, and then have storm windows put in front of them. And so working with an architect in Detroit, we started to explore the idea of, is there a product that can give us the performance of a standard IGU that can fit in these historic glazing pockets? And so I reached out to Pilkington Glass in Toledo, and they did have a Spacia product that we submitted to the State Historic Preservation Office to get approved. And we've done a lot of presentations on this glass and its application. But in this case, we were able to restore the bronze windows, clean them. We used a dry set method, repatinaed, re-waxed them, did some small threaded rod repairs, and we reglazed them all. And the beautiful thing was, this was going to be a residential building. So now I don't want to be in a building where I can't open my window, I can't get any air, but the difficulty in cleaning them, operability. It was really just a win for the client, and they are very pleased with them. There's a lot of information about this project on our website. If you're interested, on the right, this is another project we're doing with spatial glass. This is 4th Avenue. These are steel windows. This building remained occupied while we did this work. We reglazed all of these on site, stripped, repaired, a lot of body work. But the VIG, the spatial, was definitely like the less disruptive choice, less construction waste, the ability to maintain historic character. You're not, using all of your resources to fabricate these new windows. These windows have been here over 100 years. They're going to be here 100 more. Instead, you're going to buy a replacement window. You're going to have to replace them 10 years. It just didn't make sense. So I think they overall get an improvement in energy efficiency and air, and they're very happy with this. So here's that Pilkington spatial glass. You can see better. It's got a similar performance to an IGU, less impact. You're reusing existing material. You're getting energy savings. It's a great product. There are some limitations with sizes. And then there's some applications that, it's just not the right choice for. But in these cases, so in my opinion, it was. So these are 3 of the projects that you may recognize. And thank you for your time. If you have questions, or I'm happy to answer them.
Thank you so much. Yes, if anyone has any questions, you can put them in the chat.
Or try.
Someone asks, what repair metals should we stay away from when working with cast iron?
So I really feel like mild steel, right? Like there's a compatibility chart that I have that is very useful, that shows, like which metals are the best in terms of galvanic corrosion, the least resistance from the steel manual. But I would say stainless is the best in our opinion. But stay away from, I would just say steel, probably mild steel. Fiberglass, stay away from fiberglass. A lot of people like fiberglass now.
Well, so actually that was a question, because you were saying when you were repairing one piece, if you wanted to make it look like fiberglass, why would you want to make it look like fiberglass?
Meaning like perfect. Like I say that to people all the time, like this isn't plastic. You don't, I personally, like that's an unrealistic goal, right? In my opinion, is that you want it to look like the material it is. But sometimes people will question, why doesn't it look shiny and flat? And I'm like, that's because it's not fiberglass. It's not plastic. It's iron. It's porous. So I think we see a lot of that now with a GFRP and GFRC replacement. Sometimes, I can tell the difference. I don't know that a bystander can, but I can definitely tell the difference.
Yeah, no, that definitely makes sense.
Yeah.
Someone says, do you have restored cast iron fountains and fences?
We do not. We do not sell. We're a custom house, so we are on a project by project basis. We do have some fencing. We have a lot of fencing. Don't have many fountains. We don't. We're trying to kind of develop our catalog in a way that it's hard. It's hard to know how to market what you have, and a lot of times it'll be repeat clients or landmark railing projects where there's similar buildings and railings, but there's not a lot of things that we sell repeatedly. Lampposts, sell a lot of lampposts, sell a lot of canopies.
Okay.
Thank you.
Can you talk about coordination with curtain wall manufacturers at Woolworth?
Yeah, it was great. We worked with, I think they're out of business now, AIC, and they do a lot of curtain wall uh, work. They were really instrumental in coordinating because the coordination between the door manufacturers and the storefront manufacturer and the glass and the mechanical systems and everything, it was intense. But we really enjoyed working with AIC. They were great.
I was very fortunate enough to be able to see the restored cast iron in the Woolworth close up and be in one of the condo units and see the cast iron from the window, and it
Oh, yeah.
was gorgeous. You guys did an amazing job. It was beautiful.
Oh, thank you. Thank you so much.
What
Oh,
was
Tanemic coatings, we use 69 and 27, and we love Tanemic. So 1070, the 1070s are those floor nars. The 1078 is a metallic. She's asking you about the Tanemic coatings we prefer to use. Have everyone solid glass and are you talking about the glass pucks, Kara? Let me see the.
Yeah, she said yes.
Okay. Glass block. We haven't had any glass block projects, but I would like to do some of those. I think I'm trying to remember the address exactly, 4th Avenue. We work on so many, like we have 35 active projects right now, so I get a little mixed up in my head sometimes. I will find out. I'm sorry, I gotta find out. 4th Avenue project. See if I can get an answer for you.
Yeah, if you can't find it now, you can always let me know, and
Sure.
I can just
Yeah.
email Eric who asked.
Yeah. It's I can see it in my head. I just don't have the address off the top of my head. It would be on the website. Oh, thank you so much. I appreciate that.
I don't know if you saw there was one more. In one of the photos of a repair, it looked like the backplate of a Dutchman was welded. What material was used for the backplate in that situation? Also, when you were doing a stitch repair of a threaded rod repair, I assume the rods are stainless. Is that
Yes.
right? Is there a galvanic concern?
Is there a what concern?
Galvanic.
Galvan,
Galvanic.
it's very low. So the stainless is like I'm gonna send you that compatibility chart. It's definitely the best solution you have for repairs of that type. I mean, you're not gonna recreate, gray iron or rivets anymore. So you have to kind of work with the constraints of what you have. And stainless and coatings are tremendous as well as stainless. So yeah, I think we weld everything with nickel rod and the shop, unless it's aluminum, and then use stainless steel fasteners or replace them everywhere we can. Avoid steel fasteners. We had some issues where client didn't choose to use our stainless steel fasteners, use steel instead, and we had a lot of cracking and lamppost space, and so we helped them make all those repairs, but it really does make a huge difference.
Great, thank you. Well, I think that is it for the questions, and it is after 1.
Okay.
So thank you so much, Kate. This was amazing. It was very fascinating, very informative. Thank you so much, everyone, for joining us today. That was
Yeah.
great.
Thank you for
As
being here.
you are aware, this has been
Oh,
recorded. Yes.
111 4th Avenue.
Oh, there you go. 111 4th Avenue.
Thanks.
Yes, this has been recorded. It will be on our YouTube channel, as I said before, all of our other preservation schools, and we have many virtual walking tours on our YouTube channel as well. So please check that out. Once again, thank you, Kate, and hope to see everyone soon.
Bye. Thank you for your time.